Hi, welcome back. So in the last video of this module, we will talk about the principle of virtual work. You have seen it before, possibly in the statics course. Here we'll see maybe the proof, if you haven't seen it before, and why it is useful and how we can use it. So let me define it. What is this principle of virtual work? A catastatic system is in static equilibrium if and only if, so this means if and only if and only if the virtual work of all applied forces equal 0. So this is a bidirectional condition statement. So that is the if and only if. If the virtual work is 0, the system is in a static equilibrium, and if the system is in a static equilibrium, it means the virtual work of forces are 0. So there are a few things that probably you don't know what is going on. So one is this catastatic system. We also need to define what is static equilibrium. But before that, let me talk about this. Applied forces. So I don't know, let's pretend I have a system like this. A system of multiple particles and possibly parts. I have, let's add another link to be cuter. So I have a bunch of forces acting on this system. So there are these applied forces, and within each joint, there are reaction forces between bodies and particles. Here, this one says, if you want to have the system to be in a static equilibrium, the entire system be, we don't need to worry about the reaction forces. Somehow we can only work with applied forces. So if we want to go back to the Newtonian view, we have to draw a free body diagram of each body, include both the applied forces and reaction forces, and make sure the acceleration of each body is 0. So the usefulness of this principle is that useful because we can ignore reaction or constraint forces. So we don't have to calculate them and then find the balance of forces within each body. So okay, let's make a few definitions. What is catastatic system? Catastatic system. A system is catastatic if the transformation equations from q's to other coordinates xi's q's to x, q's to x's does not explicitly include time. So in other words, partial xi partial q, oh sorry, partial t is always 0. So there's no time if your x is, I don't know, some L sine of theta, that is a catastatic system. But if L is different, so x is some, I don't know, at sine of theta, when here time shows up explicitly, and now the system is what it's called, acatastatic, I think. So here we're talking about systems such that time doesn't show up in transformation equations. Another definition is what do we mean by static equilibrium? Equilibrium, this means the system is motionless, and all accelerations will be 0 at all time. So we're talking about the entire system and acceleration of every body and particle in that system. That's how we define equilibrium for the entire system. So one thing to note, it is different from a balance of forces. So this is not equal to balance of forces for the entire body. So as an example, imagine I have, I don't know, a simple mechanism like this. I have two forces equal and opposite each other. So in this case, the entire force, the total force on the system is 0, meaning that if this is center of mass, acceleration of center of mass is 0, but individual bodies may move. So this mechanism may fold, but the center of mass doesn't move. So this is not in a static equilibrium, this system. Okay, is there anything else need to be defined? No. So if I have a system that is catastatic, meaning that there are no influence from the outside, such as a link that its length is changing, that the length is prescribed to change as a function of time, and essentially a passive mechanical system. So these systems are in static equilibrium if the virtual work of all applied forces equals 0. So to prove that, so here's the proof. We have two ways to go. One is the necessary condition and the other one is the sufficient condition. So let's look at the necessary condition. Necessary condition. So we want to see if we are in a static equilibrium, does this imply virtual work is 0? So that's what we want to do as the first step. We know we have a static equilibrium. That means for each particle, or for all particles, F plus R, that is all forces acting on that particle, including the applied forces and the reaction forces, this is 0. And so from here, I can calculate virtual work of all forces is the summation of, let me actually do this. So if I have balance of all forces on all particles to be 0, I can write delta Wi to be Fi dot plus Ri dot Dri should be 0, right? Because this is 0. And I can write it as well, hold on. This has to be delta Ri because we're talking about virtual displacements. So I can write it as Fi dot delta R plus Ri dot delta R I equals 0. And we knew from before that the virtual work of the reaction forces is 0 in these systems. So that means delta W of all forces, which is this term. So this is delta W of Fi is 0. So summing over them, we get that the virtual work of all applied forces has to be 0. So that's one way. The other way is the sufficient condition. Sufficient condition the other way around. So if delta W is 0, does this mean we are in a static equilibrium? Static equilibrium. And instead of working with this, let's go in the opposite of that. So if not in a static equilibrium, does this mean delta W is not 0? And this is easier to work with. So if we are not in a static equilibrium, this means that at least for one particle, F plus R is not 0. So we can then write there is going to be at least some direction of virtual displacement consistent with the constraints of the system, such that this delta Wi, which is Fi plus Ri, delta Ri, this is a dot product, this one is not 0. And from here, we can say this one shouldn't be 0 either. So that is the proof of the principle of virtual work. You had seen this before in statics, that we were talking about virtual work to calculate the forces that act on a system for the system to remain static. Now you know why this principle works. Anything else? Let me see. No, there isn't anything else. So that's all for now for this module. In the next modules, we will be talking about how we can take these ideas, virtual displacement and virtual work, to define some generalized concepts of momentum and kinetic energy, and in the future chapters, how we can use these to derive equations of motion for the system. So until then, happy studying. I see you later.